Hello, welcome. Happy Thursday. We made it to the end of another week. Thank you for coming. Reminder that we started Lab 7 on Tuesday and you have a week to complete it because it's work outside of class because we have to keep moving. Also be working on your project. Keep in mind that there's a progress report due tomorrow night. And I advise you to be as specific as possible. So hopefully by now you have your script. Most groups have a script to say, here's how this game is going to work. And so now your job is to implement that. So decide what classes you're going to create, make a driver file, and start simple and work up. So the thing that's going to best serve you is to be as specific as possible in this progress report.
Do all members of a group have to turn in their own progress report?
Do all members have to turn it in? No, because this is it's a group assignment. Let me verify this. Yeah, it's a group assignment. So only one person needs to write it. Or the whole group can be like, this is what we did. Let me fix that. Good thing we're here. So I'm just looking for a text entry. So a few paragraphs of be as specific as possible. So you can say, we created this class, this class, this class. This is how they relate. And I can pull up your script and refer back to see, okay, this how it relates in terms of your overall goal. So be as specific as possible. And then, because if you're like, we worked on the code, that's not helpful for me. And like, we worked on the code and ran into some errors. What errors? I don't know what they are. I don't know what your code looks like. So keep in mind as you do this, if you have errors, you can come talk with me. But I encourage you to try and work it out in your groups first, because eventually you're going to have to go and write programs and there won't be a professor there to debug for you. So you need to, yeah, keep developing those skills of software development. Okay, let me save this. Okay. Today, we're talking about recursion. We're going to go over the recursion slides. And then next time, we will finish up anything we didn't cover today, and we'll do lab 8. Any questions on the plan or stacks and queues or anything before we move forward? Cool. Not dynamic programming, recursion. All right. Here's where the fun stuff starts. Who here has like talked about recursion in a previous class? Okay. A little bit, one person. Okay. So recursion is when a method calls itself. So if we have some method, let's call it, we have some function ABC that does something. If in the course of this function, we say ABC again, then ABC is a recursive function. So something that recurs is something that calls itself. So it makes a call to itself. The thing about recursion is that typically, especially at the start of this class, when I say implement this method so that it does this. So like if I give you solve ABC, sometimes I tend to see you just write return ABC and nothing else. So we kind of do this accidentally when we're starting to learn. And so now we're going to see we actually can do this. It is legal, but there's just some considerations that we need to take in mind. The main consideration is that when we do recursion, it has to call on a different or a simpler instance. So we can't just say, like, if I give you some array to do ABC on this array, I can't give it the same array. So we can't just like do the same thing over and over and over and over again because we're not getting any work done, right? We have to progress and do things simpler, simpler, simpler so that we can actually finish. That's the goal. One example is, let's say we want to examine all files in a directory. So let me pull up a directory. Actually, I think, yeah, this will work. But let's make a new one so I don't mess it up.
Wait, are we doing a new package?
No, not yet. Okay, so for example, here's a directory. I've got a directory full of the records from each of my Zoom meetings, right? And so one way to, let's say I want to process this and like maybe get the recordings for each of them. So how do I do this? So I can have a for loop and say like start at the first directory and go to the next one and go to the next one and go to the next one. So I can do this iteratively, or I could do it recursively, which means I want to examine all the files in this directory, and there's some level of, I need to break it down a little bit. So what I can do is I can say, let's take this first one, and I will process all the things in this first one. So I go in there, and that's, I think, the current one that we're in. And so we can process, okay, let's go through each file, and now we have the recording. Great, we're good to go. So I've moved back up and I'll go through the next one. So here's the meeting. I can find that recording and process it. So it's a recursive process where in order to go through this folder, I have to go through each of these subfolders. Let's take another example. So let's say that this is my 222 folder, and some of these folders have subfolders. So like, let's take lab projects. There's subfolders in here. And so I need to take the same approach of, if I'm going to process this folder, I need to go through all the subfolders. And so here I am in a folder, and I need to go through all the subfolders. So maybe lab 2. I have folders, need to go through all the subfolders. So we can go in recursively and do this. And then the key is, once we get to a point where we've got all files, great, we're done with this folder. And then we move back up a level. And then we go through test and we come back here. Great, we're done with this. Let's move up a level and go through the other folders. That's a recursive process. Let's say we also want to look up a word in a dictionary. So I have an example here. I wrote that example when I looked it up on Google. I'm going to try using the dictionary app. So let's say I want to define boon, which means a thing that is helpful or beneficial. Maybe I'm going through this process and I'm like, I don't know what beneficial means. I should look that up. So if we look up beneficial, then it says, oh, it's favorable or advantageous, resulting in good. I don't know what advantageous means. Let me look that up. And so involving or creating favorable circumstances that increase the chances of success or effectiveness. Let's say I know what this means now. This helps me to bring it back up. So if I go back to, no, so it was beneficial, then advantageous. So now that I know what advantageous means, I can bring that back to the definition of beneficial. And so, advantageous, it helps me create a good situation. That's what beneficial means. Then I can use the definition of beneficial to help me say, oh, that's what boon means. So now I know what this means through a recursive process where I break it down into smaller problems where I choose one of the words in the definition that I don't know, and I go down the process of figuring out what does this word mean? What does this word mean? And then I can bring that back up so I can understand the original word. So the reason we talk about this is that there are a lot of efficient solutions that are based on recursion, where this notion of I want to solve this problem, but it has sub-problems. So sub-problems where we're doing the same thing. And so maybe it's easier to calculate this recursively rather than iteratively. So one example I have here is factorial. Does anybody know what factorial is? What is it?
Also to be like, for example, if we get five in a factorial symbol, how that works is that it would be 5 times 4 times 3 times 2 times 1. And then I guess it kind of gets exponentially larger, the larger you want, I guess, the larger the number is.
Yeah, I think it's worse than exponential. Like factorial is its own class. Yeah. So the idea of 5 factorial, you're right, 5 times 4 times 3 times 2 times 1. And so then the way we write this generally is, let's say we have n factorial. So this is not us being excited about numbers, although we can absolutely be excited about numbers. The exclamation point means factorial. So that's n times n minus 1 times n minus 2, and so on, until we get to 1. But the thing is, this is recursive, because we have n, and then what's this? So if we have 5 factorial, and we take 5 and multiply it times 4, 3, 2, 1, what's this part of that? Yeah, it's 4 factorial. And so the way we can write this long string of multiplications in terms of n factorial, it's n times n minus 1 factorial. This is recursion, where we're doing the same thing. We're still doing the factorial operation on n minus 1. So if we are computing 5 factorial, so we're like, okay, let's multiply 5 times whatever 4 factorial is. And then in 4 factorial, this is 4 times whatever 3 factorial is. And then 3 factorial is 3 times whatever 2 factorial is, right? We can break it down, go down the chain. 2 factorial is 2 times whatever 1 factorial is. And here's where we reach our stopping point, where the way we define this is that 0 factorial and 1 factorial are both equal to 1. So this is what we call a base case. So 2 times 1 factorial, that's just 1. And so now we can do this multiplication of, I know what 2 times 1 is. I know how to multiply things. That's just 2. And then we say, okay, now I have a solution for 2 factorial. I can multiply 2 times 3. That's 6. And then we say, I know what 4 times 6 is. It's 24, I think. I can't do math when I'm up here. And then we do that, and then we multiply by 5, which I definitely don't know that off the top of my head. Does someone know what it is? 120? Yeah. Is that 100? Something like that. So the point is, once we do this recursive call, and we work our way down to the simplest instance. And then what we do is we go back up and we say, I've solved this simpler problem. Let's apply that to what was asking for it. I've solved this simpler problem. Let's kick it up the chain. So it's like if a boss is like, I want to do this project, and so gives it to the managers. And the managers breaks it down into these are the things that you teams are going to do. And then the teams break it down into you do this, you do this, you do this. And so once all of those are finished, they send it back up to the manager, who sends it, or the team leader, who sends it back up to the manager. When all of those things are done, they give it back to the boss. So it's this idea of we break down problems until we give someone a problem that they can be like, yep, I've done it. Here it is. And they pass it back up. Questions on this so far?
We're going to get to
Coding?
actually code this factorial function.
Yes, we will. We're talking about it conceptually first because it sucks a little. So we need to figure out what we're doing before we actually code it. Actually, you make a good point. Let's code this one.
We're creating
Yeah, sure. Okay, let me pull up Eclipse. So I'm making a class. I'll put it in, I don't know, recursion. So what I'm gonna do, I'm gonna make one file for all my recursive functions, because it's gonna be like a lot of little functions. So I'll call it recursive test, and I'll give it a main, because I'm just gonna be testing things. Okay,
for you or
yes. Okay, I'm gonna write my factorial function. So since this is a demo class, we're gonna need a static method because there's no controlling recursion test object. So I'll name it factorial. And the type, the return type, let's say int. We're gonna see this in a second. So factorial, it's gonna return something. And so what we could do this iteratively, right? Where we can say for int I equals 0, or maybe it makes sense to start at n.
maybe
N greater than 0, 0, 1, I don't think it matters. I minus minus, where we can say val times equals I. So we start at n, and so we'll say, let's say n is 5, so we'll have 5, and we'll multiply 1 times 5 is 5. Then we go to 4, 5 times 4, then 4 times 3, 3 times 2, 2 times 1, until we get to not n greater than 0, I greater than 0. I think this should work. Let's test it. Bless you. Okay, so we're doing this iteratively, and we're printing the result. So if we do 5, we get 120. Go away, zoom. We do 4, we get 24. We do 6, we get 720. We do 7, get 5,040. What are you doing? We start I at n, then say, well, as long as I is greater than 0, subtract 1 from I. Do we start val at 1?
Yeah.
Do we multiply val times I? We return it. Then do we have the print statement like this?
Yeah, it's like that.
Okay. Anybody else having issues? All right. Let me come look at that in a second. So as we increase numbers, the numbers get bigger. Where 15 is this crazy big number, let's try 30. That doesn't break it yet. Let's try maybe 50. There should be. Haha, we did it. So there comes a point when we get 0. If we try 56, something bigger than that, we also get 0. This is very, very likely that we have hit the integer overflow, which means that we have a number that's too big for int. So maybe like one possibility is to store this as a long. And then once we do that, it's because remember the types of integers are, it's the amount of precision. One of the things in the lab that you'll see the type big integer, which is a Java defined class that lets us store really big integers. So even bigger than longs. So as big as they need to be, we can store those. So you'll see that. All right, let me come see what the error is. Okay, so that's our iterative solution. Now let's do it recursively. So I'm gonna rename this refactor, rename, factorial, iterative. The way I got there is I right-clicked on the name and then went down to refactor, rename. If you're in VS Code, probably a rename symbol is what typically works. But that just makes it so that I not only change this name, but also that name. Okay, let's do this. Yeah, question? Right click. Refactor. Or I think you need to select it. Refactor. Rename.
Oh, wait.
Did you solve it?
Okay.
All right. Let's do this a different way. Where we don't need a for loop. We don't need val or whatever.
Yes.
We just need n times factorial of n minus 1. This is a recursive function. So maybe if that's it, let's test it. So I'm going to change factorial. First, let's give it 5. Then instead of factorial iterative, I'm just going to change it to regular recursive factorial. So did I. Stack Overflow error. Oh no. Okay, we have made, okay, there's a few things to talk about here. So first off, what is the error? It says Stack Overflow error.
But we didn't stop the proverbial loop
Yes,
by the time it hits 0 and
yes, that is the answer. So we say return n times factorial of n minus 1, and we go forever and ever and ever and ever. So n starts at 5 and it goes down to 0, and it keeps going because we haven't said, hey, stop. So it keeps going forever. And the way that we see this is it says Stack Overflow error, and we can scroll down, scroll down, scroll down. It's factorial that's giving us, which means it's repeatedly calling factorial. And so the Stack Overflow error, we'll talk about this. So you know how I said that when you run programs, they're stored in a call stack, right? Where there's like whenever you say, let's compute a function, it gets added to the call stack. Stack Overflow is when there's too many things there. So if we have our Pringles can and we decided to start adding Pringles and Pringles and Pringles, eventually there's too many Pringles and is overflowed. And so at that point, then the compiler is like, no, I'm going to stop you right there. You're doing too much. So the way we solve this is we need a base case. And so this can look different ways depending on how efficient we want to make this code. The simplest way is we can say if n is equal to 0 or n is equal to 1, then return 1. So we have to be able to stop it and cut it off and say, here, no more. So if we do that, now that gives us 120. So this is our base case where we say, here's the simplest possible way we can solve this. And then we have the recursive call, and it's recursive because we're in a function called factorial, and we call factorial again. This is why this function is recursive. This function is iterative because we're iterating, we use a for loop. And it's not recursive because factorial iterative doesn't show up here anywhere. But yeah, this works. So this is the sort of thing when you're first learning coding and you just like type the function name. I'm like, we'll get to that later. And the reason that that doesn't work is you're just like giving it the same data and not reducing it at all and not stopping. So these are our two main components, the base case and the recursive call. Let's try 50. Okay. So when we wait, did I say long?
what it gave me a negative number.
Yeah. Okay, so here's why I think this is happening. So it gives us a negative number, and this tells us that we have also hit the integer overflow. And I suspect the reason why I think is because we're taking this value as an integer, and then we are returning an integer times this, and since n is an integer, then it's continually doing integer multiplication instead of long. So I don't know if this is going to work. Maybe we cast it to a long. Nope, that doesn't work. The other option is to take in n as a long. That doesn't work either.
If it's overflowing into negative values.
Yeah, so maybe but the thing is, We did factorial. Iterative. Yeah, okay, so I think factorial of 50 is just too big. We did factorial of 30. Still too big.
But less negative number is giving you, or negative, because it's getting closer to the underflow limit.
Yeah, so there's a point at which that this number, because
Oh, hey, wait,
factorial is huge once you get past very small values. And so it's very easy to quickly reach that limit where we're too big even for
I
longs.
found the limits.
What's the limit?
The maximum is 20.
20, okay, so one is 20, one's 21. Yeah, there you go. Yeah, and so this is not this is not necessarily by nature of recursion. This is by nature of factorial and what we're doing. Because we're multiplying all these numbers so they get really, really big, really, really quickly. Okay. Questions about factorial? Okay, let's keep going. So how many of you are in or have taken Calc 2? Okay. Does this sort of thing look kind of familiar? Yeah. Okay. If you're not in Calc 2, don't worry. I just want to tell you that this is something, these two concepts are connected, right? So this, it's not going to be on the test or anything. I just want to say these are things like mathematics and computer science are intricately linked, and this is one of the ways where in math, we have this idea of we want to prove something, and one way to prove it is by induction. And the way we do that is you have a base case, you have an inductive hypothesis, and you have an inductive step where you say, I've assumed that it works up till now. Let's prove it works for one step after that. So for example, let's say we want to prove that the sum of n integers, so the sum of however many successive integers is equal to this nice, beautiful formula. So that way we don't have to actually go and add all of them up. If we know what n is, if we know where we're stopping, we can just use this formula and don't have to do any of that more complicated things. If you haven't taken Calc 2, this is probably scary. It shouldn't be. This thing, this capital thing, it's a Greek sigma. So it's capital S sigma.
I swear to God, if anyone makes it,
So the name of the Greek letter is sigma. And the way that this works, it's like a for loop. You know, we're a for loop where we start somewhere and we go until something, and then we just add one until we get there. That's what this is doing. So we're saying, we say for int I starting at 1, that's the 1 there. And then we go until I is less than or equal to n. And then we add 1 to I. That's what this is. It's just a for loop. And the thing is we're adding I each time. So I plus equals, or no, we need an external variable. Let's call it val. So we're saying val plus equals I. That's what we're doing. So each time we're adding the value of I. And we know that because we start I at 1 and we go up to n. And so if we've got this loop, then we'll, so val is initially 0, we add 1, then we add 2, then we add 3, and so on. So that's explaining what this is doing. We want to prove this by induction. So I'm going to walk you through. We have a base case, an inductive hypothesis, and an inductive step. Again, this isn't going to be on the final or anything. I just want to show you. Okay. So when we do this sort of thing, it's super complicated. We need a way to break it down to its simplest possible elements. And so looking at this, what's the simplest possible thing we can say?
The what possible thing?
The simplest possible way we can solve. If I say, give me the sum of blank numbers, what's the answer you can give? What's the value of blank where you don't have to do any work? Give me the sum of one number. That is 1. If I ask, give me the sum of the numbers up to 1, starting at 1, you're like, I know that. That's easy. So our base case is when I is 1. And so the base case, so the sum of one number is just 1, no work required. And so we can say the sum of I equals 1 up to 1 of I is just the number 1. So actually we'll say n equals 1. And so then we're going to plug this into the formula and make sure it makes sense. So 1 times 1 plus 1 over 2 is 1 times 2 over 2, which is 1. With me so far? So the base case for n equals 1, we know what that sum is. We can calculate it by hand. And we can plug it into the formula to verify that it is indeed 1. Base case, check. Now we need the inductive hypothesis, which basically says we're going to assume that it works up to some point. I don't know what it is. Let's call it k. So it works up to n equals k. And this is our hope and pray, where we say, when n equals k, since I verified the base case, I'm going to assume it works up to a certain point. I don't want to say specifically what that point is, because we're trying to prove it in the general case, but we're assuming that it works up to k. So this is the process of proving things, where we have some assumption, and then we try and figure out, okay, what does that mean? How do we use what we've assumed to get us to the end point? So when we look at this, so we're going up to k, and so we can write this sum out as, so the sum is equal to 1 plus 2 plus 3 plus 4 plus whatever, all the way up to k, because we've assumed that it works. And since we're assuming that it works, that this long nasty sum is equal to this nice formula, we can say that we've got k times k plus 1 over 2. We're assuming that this works. Inductive hypothesis is done. Now we have the inductive step, which is where we say that n is equal to k plus 1. So we're going 1 more than what we've assumed. And we can't just say like, okay, yeah, it works. We have to show it. So we have to dust off our algebra skills. So our sum looks like something 1 plus 2 plus da-da-da plus k, because we're working with k plus 1. And so we just add k plus 1 onto the end there. And we want to show that looks like k plus 1 times k plus 1 over 2. That's our goal. When we reach something that looks like that, then we'll be good. The thing is, we know what this part of that sum is. We've worked ourselves up there. And so we know that this bit is equal to k times k plus 1 over 2. So we can say k times k plus 1 over 2 and just add k plus 1 there on the end. And so now it's just algebra, right? So we combine the fractions, multiply this by 2 over 2. And so we have k times k plus 1 plus 2 times k plus 1. And now we can combine that over the same denominator. And so we've got k plus 1 here. We can factor that out of both terms. K plus 1 times k plus 2 over 2. Are we done? The answer is yes. We have arrived. The reason is we've set n equal to k plus 1. So look, we've got that there. We've got k plus 2 is really k plus 1 plus 1. So we've got n plus 1 here. And we've got a 2 down here. We did it. So because we've come to this form, we are done. And we have proved that for the general case, this formula is going to work for any integer that we give it. Okay, so the reason this relates to recursion is recursion has a base case, and it has this step of let's do this same process. And so if you are in a situation where you want to prove that a recursive method works, proof by induction is a good strategy to do that. Yeah. Questions on that? Okay. All right, so that's our math tangent for the day. In terms of the rules of recursion, rule number 1 is you always need a base case. So that's a rule that I violated at first, where I had this and I didn't have my base case. Thumbs down. So you must have at least one base case that can be solved without recursion. So that's our n equals 1, our simplest possible way we can solve this. This is like if we're breaking up tasks at the job, eventually you give it to an intern who's like, yeah, I can do that, no problem. Check. Here you go. That's the laziest possible option. We want to have at least one of those where we don't have to do any work, because that becomes our stopping point. So that's rule number 1. Rule number 2 is we must make progress, which means that any recursive call must progress towards a base case. So if we're working with numbers and we want to get like down to 0, then we probably want to make the number that we're calling it on smaller. If we're working with arrays, maybe we want to shrink the portion of the array that we're looking at. It depends on what we're working with, but the idea is we have to work on smaller instances of the problem. There's an example, which you may see on the final exam, which is one of my favorite recursive processes. The Collat's conjecture is something where we can, if we're given a number, we can find the sequence of this. And so the way we find the sequence is, let's say we start at 5. And if the number is odd, then we multiply it by 3 and add 1. So 5 times 3 is 15, and add 1, we get 16. Then if the number is even, we just divide it by 2. So that gives us 8. And then 8's even, so we divide it by 2, and we get 4. 4 is even, divided by 2, we get 2. 2's even, divided by 2, and get 1. 1's odd, multiply it by 3, and add 1. That gives us 4. And so the Collatz conjecture is that any number that we give it is eventually going to end in this 4-2-1 sequence. So we can write this recursively, where we say if odd, then we do Collatz of 3n plus 1. Otherwise, if it's even, Collatz of n divided by 2. And so this one violates rule number 2. Why is that? Which step are we violating? Rule number 2. Which one are we making it smaller? Yeah, if it's even, we're dividing it by 2. That makes the number smaller. 8 goes to 4. But 3n plus 1, we're increasing it, right? And I don't know that that's I don't know what that's going to give us. So dividing by 2, great. Multiplying it and adding 1, not so great, because we're not working always on a smaller instance of the problem. So it's a mathematical conjecture that this will always go down to our base case. But if you figure out a way to prove that, then you get an instant PhD. Okay, so that's rule number 2, make progress. You have to, the rule number 3 is you got to believe, which my interpretation of that is you have to be very careful in how you are structuring a recursive problem, right? You have to put a lot of thought in. You have to come up with an example and walk through it. So always assume the recursive call works and put thought into it and see, here's what I'm doing at this step, see how it breaks down. This is my same advice as for linked lists, where if you draw it on paper, then it's much more likely that you'll find whatever bugs are happening, because bugs happen in recursion a lot. So draw it out, write what you're doing, and you'll get there. And then number 4, which we'll talk about in a bit, is compound interest, which is don't duplicate work by solving the same instance of a problem in separate recursive calls. We'll see an example of this. But first, we'll do some practice. So we did factorial. So I would like you to talk with your neighbors for a bit and focus first on the sum of n numbers, where I want to, so like with factorial, do it iteratively, where just no recursion required, and then tackle it recursively. Okay, so turn to your neighbors. I can pull up factorial again if you need it. But yeah, take a few minutes and write both of those functions. Go for it. So let's code this. Let's have it be int. And then I'll call it sum it for iterative. And I want to add numbers 1 plus 2 plus so on and so forth up to n. That's my goal. And so if I'm using a for loop, either we can start from n and work backwards. So we can do like n plus n minus 1 plus so on and so forth until we get to 1. Or we can do 1 plus 2 plus so on and so forth up to n. Do you see how it's two ways of getting there? Either we start from 1 and work our way up, or we start at n and work our way down. Eventually, we'll stop either way. So since we did the n and work our way down for factorial, let's do that again here. Again, if you choose to do it this way, that's perfectly fine. That may be the way that I first approach it. But I want to do it this way because it applies to the recursive version more smoothly. So we start at n. As long as n is greater than 1. Oh yeah. So let's say n goes until 0. That will include 1. And then decrease, decrement. We need somewhere to start, so we'll start some variable sum at 0. And then we'll say sum plus equals I. All right, bless you. That's how we do this. And then at the end, we just return sum. That's our iterative way of doing it. We can also do this recursively, though. So if we decided to start at n, this is kind of where the same idea as factorial comes in. Where we start at n, and then we wanted to know the sum of numbers from 1 up to n. That's going to be equal to n plus whatever the sum of n numbers is up to n minus 1. Because it's n plus, we've got n plus n minus 1 plus n minus 2 plus so forth until 1. This is the sum of n numbers up to n minus 1. This is the sum up to n minus 2, and so on. So we're recursive. We break it down at each step like that. That's how we construct the recursive function. So this is my recursive version. And we need a base case. So we want to add the numbers from 1 to n. So let's say if n is equal to 1, then return 1. And again, this is the simplest possible way we can solve this problem. So the base case from the proof is the same as the base case for the recursion, where if you give me the number 1, I don't need to do any adding to have the result. I can just give it back to you. Otherwise, it's going to be the same structure as recursion, as factorial. Where we're starting at n and we work our way down. So let's say we wanted to structure it the other way, where we wanted to start at 1 and work our way up. Hmm. Call it ASC for ascending. So, any ideas? So we don't have to spend too much time on this. Just something to take home and think about. I think the answer would probably be is if we have an extra parameter for like the limit and that helps us know when to stop. But I think the easiest way to approach this is to start at n and work our way down, where we can define, here's what this subproblem looks like. If I'm trying to add n numbers, I just add n and then whatever the sum of n numbers up to n minus 1. And then that's the sum up to n minus 2. That's the sum up to n minus 3, and work our way down. Questions on that? Okay. So let's say I want to print some numbers in ascending order. So instead of adding them, I just want to print them. So let's start with ascending. So if I've got a function to add all these things, what do I need to change to print them? So I'm just going to copy that and put it down here. So I'm going to call print ASC for ascending, then underscore IT for iterative. So if I'm not adding them and I just want to print them, what do I change? Especially if I want to, let's say I want to print 1, 2, and so on up to n. How do we do that iteratively? What do I need to change here? Yeah,
Sum plus equals should just be printed on.
yeah. Okay. I also just remembered that we never tested the sums, so let's do that before we move on. So yes. Okay. For some reason, okay, let's comment those out. We want to print these. Have I named the functions correctly? I believe so. So, okay, so something's wrong. Because the red square comes up, and so nothing's happening. Let's see if it's one or the other. Okay, so something's wrong with my iterative function. what is it? Ah, I know what it is.
Wait, wait, which one had the problem?
This one has a problem. Yeah, and if I give it n of 5, n is never going to be greater than 0. So what do I need it to be? Yeah, yes. If I do that, then that gives me 15. So now let's try the recursive version too. And it also gives me 15. Hooray. Cool. Okay, so let's go back to print. So since I copied garbage, I have to change what I copied. So this has to be I as well. We don't need sum at all. So we can get rid of that. And we don't really need to return anything. So we just want to print something. So is this going to print things in ascending order?
Descending. It looks like it's going to print it in descending order
That's correct. Why is that?
because it's a subtractive for loop instead of
Yeah,
Hmm,
so we
yeah.
start at n instead of at 0. So we've done the work for print descending, but let's change this one. So I is, as long as I is less than or equal to n. So we have to change this around. So since we want to start at 1, we have to start at 1. We want to go up to including n, we have to say less than or equal to n. And then we have, since we're going up instead of going down, we have to add 1. Is this going to give us what we want? No? Why not? Do we do that? Don't we do that? Because, yeah. Do we think we're good? Let's test. Oh, wait, no, that doesn't make sense to print it. Because this doesn't return anything. It's a return type of void. So let's just get rid of that extra parenthesis and just call it. So we've set this up to just print something and not return anything. Okay, so I'm calling that. Let's see if it works. And it prints 1, 2, 3, 4, 5. Maybe if we wanted to have it all on one line, we could say print it with spaces. That may just be semantics. The point is it prints things in ascending order. So we're good? Cool, let's do it recursively. Okay. Okay, I will note that, so in my notes, I have a lot of different versions. I have like 3 different ways that we do this. So yeah, I think descending is easier. Well, maybe descending is easier. Let's do descending first. So if we want to copy this for descending, and so then we just DESC instead, then we just change the for loop back to what it was before. So n, as long as I is greater than 0, subtract 1. Right, so just changing the terms of our for loop. Let's run that just to verify. If I do that, then it prints 5, 4, 3, 2, 1 instead. Great. So if I want to do this recursively, what do you think I need to do? So if I'm starting at I'm starting at n, it's going to be the same idea where first I print n, then I'm going to say, okay, print desk, you cover the rest of them, starting at n minus 1. So if it's going to be the same sort of function as we've written before, where we have n and then we call it recursively on n minus 1, making it smaller each time, we need a base case. And our base case can be if, let's see. I could just say if n is equal 0. I could say if n is less than or equal to 0. If maybe there's a case where I could be given a negative number, I would say that is more safe. And then maybe I want to print done and return. Return meaning we're done with this void function, don't do anything else. That's my base case. For the recursive call, let's first say we want to print this number. So we're printing n, whatever we're given. And then we pass n minus 1 to this same function. So this is the key of recursion is being able to break this up into sub-problems. This is something that I'm going over with my students in 374, the analysis of algorithms class as well. So you're both kind of doing recursion at the same time, which is they're working on dynamic programming, which uses recursion to solve these really complex problems. And the key here is to be able to break it into subproblems. So if we want to print n numbers, so like, let's say we want to print 50 numbers. The question is, how do we break it down? So we want to print 50 numbers. How can we print just one right now? Like just a single number. And so that ends up being this step. Just print whatever number we're given. And then we hand off the rest to the recursive call. And it's like, okay, you handle the rest of these. And so what ends up happening is we print, like, let's say we call this with 5. So we print 5, and then we call print desk of 5 minus 1, which is 4. And what does that do? It prints 4, and then it calls print desk of 4 minus 1, which is 3. What does that do? It prints 3, then it calls print desk of 3 minus 1, which is 2. And so on until we get to print desk of, let's see. So our base case is less than or equal to 0. So print desk of 1 gives us 1. And then calls print desk of 1 minus 1, which is 0. That's the point when we hit the base case. And we say, done. And then we're like, okay, print desk of 0, check, you're done. And then at that point, since print desk of 1 called print desk of 0, 1 is done. And so it goes back up the chain. We're handing the work back to our bosses of, I'm done with my work, I'll give it to my boss. The boss says, okay, I'm done with my work, give it to their boss, and so on. So it goes all the way back up until print desk of 4 finishes, and then it's like, here, I have printed all of these numbers.
Also figuring out how to make
The descending,
descending, like the numbers in the list go in a sideways order instead of downwards,
in a sideways order instead of downwards.
like on the same line.
After class, show me, I'm interested. Okay, so let's call the recursive version. This prints 5, 4, 3, 2, 1, done. Prints them all on one line. So maybe we do the same thing where we add a space there. Nope, that didn't do anything because we're still calling print.
That's because you're still.
Yeah, we had an end line there. Once we do that,
Oh, wait, never mind, that you already did it.
yeah. So we call print instead of println. Cool. So let's say we don't want to print anything. Let's say we just finish there. I'm going to argue that if we want to print in ascending order, so instead of print desk recursive, print ASC recursive. In order to do this, my bold claim is that we've got these 2 lines. My bold claim is that if we swap them, it's going to give us what we want. So like if we do this, it's going to give us what we want. Who agrees with this or who thinks this is crazy?
You're insane.
It's recursion. Let's test it and then we'll talk about it. So ASC recursive. 1, 2, 4, 5, 4, 3, 2, 1. Okay, so maybe not quite. Maybe we didn't quite get there. But maybe we almost got there.
Wait a second. Try putting, try swapping the index system.out.print, no ls statement. Try swapping the places of the n and the quotation mark of the space in between.
Okay, so do the space first.
Oh, never mind.
No, that just pushes 5 over. Okay, so do I have? I think this is what I have. Yes. Okay, it's slightly what I have. How much time do we have? 5. What happens if we just print ln? Am I calling the right thing? Okay. So I have code here that I copied when we wrote, yeah.
I'm so print this.
Yeah. Thank you. This is, yeah. Recursion gives, there's so many opportunities for stupid errors. That was it. Thank you very much. So, I still get 1, 2, 3, 4, 5. Okay, let's do this. So this is something that you should do when your recursion isn't working. So I've got one version of this over there and another version of this over here. So let's compare the two. No, go back. Okay, so let's assume n starts at 5, right? We're going to draw this out. So we go here and ask, is n less than or equal to 0? N is 5, so the answer is no. So then we go into, print ascending recursively of n minus 1. So we call this for n minus 1, which is 4. And so when we do this, now n is 4. And so we ask, is it less than or equal to 0? No. So then we call it recursively. N minus 1 is 3. And this continues. So print ascending of 2, and then print ascending of 1, and then print ascending of 0. We get here, and so we print nothing. So we go to a new line, because that's print ln, and then we're done with PA of 0. Now we're in PA of 1, so we've done this part. Check. Now we have one more line to do in this function, which is print a space and then the number n. So we print a space and then the number, which is 1. And then we're done. And then we print, and then we're in PA of 2. We have done print ascending of 1. So now that's all left to do is we print 2. So the question is, on which side do we do it? So this gives us, and this is kind of what we're seeing. So what's happening is we see space, we see the enter, so there's a blank line here, and then we see the space and then 1. So my bold claim is kind of crazy because it's a little bit crazy because it is giving me this printing in ascending order, right? It's giving me 1, 2, 3, 4, 5. Just maybe the formatting is a little weird. Okay, so turn in this file, your recursion test.java for active learning.
But we didn't figure out the.
Yeah, so we will finish this next time. Next time we'll fix all this weird spacing stuff. And then we will look at,
Okay.
so we'll finish this next time. We'll finish this slide deck and then we'll go into the lab. So turn in your recursion test or whatever you've named it. Turn in that file for active learning and I will see you on Tuesday.
Okay.
Yep.
And